Welcome back, everybody. This is the S.A.G.E website, and it shows you the website. It's a collection of freely available compiled C++ programs that perform a wide variety of both analyses, both on family data and on individual data. So the current, are you going to do this slide, Yunju, or am I? Yunju, are you there? You're going to do this slide, weren't you? Right?
Yeah, I can do that.
Yeah.
The current version of the S.A.G.E is 6.4.2, which is released in February of this year. The S.A.G.E programs can be run either from a command line or from a class platform, the graphical user interface, which is GUI, that is included as a part of the complete packages. S.A.G.E requires 1 GB of free disk space and at least 256 MB of RAM to be able to actually install. Along with the source code available in the S.A.G.E website, which you can access through the link in the main website, the precompiled and tested binary executables are available for the Linux and the Windows platforms. Unfortunately, right now, the Mac is not available. And online help and support can be requested through the link in the main website, which is shown in here.
All right. So this is how S.A.G.E works. You basically have the S.A.G.E program in the middle. You have to input your pedigree data. You input what is known as a parameter file, .par. That gives you all the analysis options. You may have to input other files. And then you have 3 possible outputs. The first output is the .inf file, and that is what you should look at first because it indicates if there's any errors. And if there's any errors, you don't want to look any further. Then you have the analysis results file. And then there may be another output file, which you might want to need as input to one of the other S.A.G.E programs. This is the roadmap. As you can see, there is the roadmap to the S.A.G.E graphical user interface, or the GUI. And you can see there are all sorts of programs. The top row are data summary and quality. There's PedInfo, Freak, Marker Info, and RelTest. I'll talk about those in a minute. Then there are aggregation and segregation programs that they're called FCore and SEGREG respectively. And then there's model-free linkage programs, and they're called GenIBD, SUDPAL, LODPAL, REDPAL, and AJAR. There's also a program, Despair, and that one is not available in the GUI. It's an online program that helps you design a linkage analysis, a 2-stage linkage analysis. And then on the last line but one, you have the model-based linkage programs, LODLINK and MLOD. And right at the end, on the last line, you have the association programs, TDTX, S.A.G.E, and Decipher. So there are all sorts of variables you can have. Let me, first of all, there's the ones that tell you about the pedigree, the individual and parents, and those we'll see in a minute. Now, you have a pedigree or family, And within that, you an identification for that pedigree or family, some number, and then within that, an individual, and then you have parent 1 and parent 2 of that individual. Then you have a sex field, the sex of the individual you're talking about. Then you can have traits, phenotypes, covariates, and then you have the question, well, what's the difference between a trait and a covariate? Well, you want to use a trait is for any variable that you want to analyze. It wants to be the main trait for analysis. Phenotype and covariate are more what you might want for specific analysis. Now, trait is program specific in a sense, in that some programs will automatically analyze all the traits, either one after the other or as a multivariate trait. Whereas the phenotypes and covariates, they're only specific to that particular run. Then you have markers, and you have alleles, and it requires a locus name to link the alleles, and you can have what is known as a trait marker. We'll discuss that a lot later on, because a trait marker, first of all, you've got to remember all markers are really phenotypes. You never know the genotype of a marker. So it's a special kind of trait in a way, because it's something you observe, and so we call it a trait marker. Then you can have text and other unspecified material. Now, on this slide, you can see, first of all, you can see the essential pedigree structure fields on the left. You have, it's called family and individual. Family is the same as pedigree here. So it's in family number 1, 2, 5, 6. Individual number 2046, whose father, that's an individual with a father in the same family, obviously, 3146, and a mother 3046. This individual is male, has a trait called unaffection with the value U, has an aged exam, here 48. The dot here has been specified to be unknown, so unknown age of onset, unknown DBH value. DBH is dopamine beta hydroxylase. Also in this file, we have the square root of dopamine beta hydroxylase. And then we have two factors we call factor A and factor B. And then from N onwards, you have a whole bunch of marker, and these are marker phenotypes. And we're told here, we'll talk about it later, this is a one column format. Each marker has 2 alleles, and the delimiter / separates the 2 alleles. So the third row down, you see that individual has alleles 2 and 1. Okay, and those are basically marker phenotypes. I think we can go straight on from here. So this is how the data fields are interpreted. You can read section 3.2.5 from 2 of the user reference manual to get more information. But ideally, you have the pedigree ID field, you have it there. You have the 2 parents ID fields, and you have the sex field. This is optimal, and no special interpretation applied. However, if the sex field is missing on the second row, you see pedigree ID field and 2 parent ID fields are there, the sex field missing, then clearly you cannot do any analyses that are sex dependent. So this means this, for this analysis, it would be invalid for sex dependent analyses. Then the next row, you can see it just says pedigree ID field. And it also has sex field. This suggests that all it's a common pedigree, but you've got the 2 sex fields, so they're all full SIBs. On the other hand, in the next line, you see the pedigree ID is not there. You just have the 2 parent ID fields and the sex field, and it assigns all individuals to one single pedigree. But it doesn't know who are parents. So it's really like one huge SIP ship, if you like. Next one, you just have the pedigree ID field, nothing else. This may require what's known as the treat as SIBS option. It's invalid for sex-dependent analyses. The next one, where all you have is the sex field, all individuals are assigned to one single pedigree. And the last one, where they have the two parent ID fields and nothing else, all individuals are assigned to one large SIB ship, and it's invalid for sex-dependent analyses. There's more, I mean, typically you will not use these unless you know what you're doing. And if there's nothing there, nothing at all in those for either of those three fields, then again, all individuals are assigned to one single pedigree, and it's invalid for sex-dependent analyses. Okay, let's go on. And we can see on this slide, we have a family ID in column A, an individual in column B, a father in column C, a mother in column D. And you can see in this analysis, a dot has been, you have already basically assigned a dot to be a missing value. Then you have the sex ID, and you've assigned M for male and F for female. You can assign anything you want for male and female. Eventually, SAGE is going to change them into ones and zeros. Then you have affection status, and you've decided you will be unaffected, A will be unaffected, and dot is missing. You have aged exam, and you have these various ages in the column G. And then in column H, you have age of onset, which is missing for a lot of people. Then you have the value of dopamine beta hydroxylase called DBH, and you'll see it in this on this slide. All those individuals you can see there have it missing, and then you have another column J for the square root, and they're all missing. And then you have two factors, and we'll talk about those later on. We're going to call them factor A and factor B. Sometimes they're there, sometimes they're missing. And you see where you have missing values for an allele, a dot. Okay. This is where you take over. Is that right? Okay, take over.
Okay. Most of you probably know how to save an Excel file as a tab delimited text file. But just in case you may not know, or maybe need a reminder, that I'm showing you right here. So you select, after you go to the save, you select save as, and then within here, save as type. There are many different types that you can select, but you select text tab delimited type from this drop-down list of the save as option in Excel. That's how you actually make a save the Excel file to a text file, which this case is tab delimited file. And also in case if you want to save it as like a comma delimited file, there is another option called like a CSV comma delimited .csv file type. So you can do that too. So the reason that we are going through this one is because for the pedigree file, SAGE accepts a variety of different input data formats, which is like a first case, there is a text character delimited file. It's just like by either tab or comma or some special character or others. So in case it's other, you can actually type in these other characters. And also those delimiter can be single or multiple, or you can use the Excel file as it is and then specify whether it has the header or not. But right now, you like for the as a like a note, this Excel file type that the SAGE can accept is actually old Excel file type, which ends with like a .xls. Okay, but the newer version of Excel, which ends with like a .xlsx, does not have it actually has some like IO errors. So if you want to use the Excel type, to make sure that you use .xlx file. And then you can use, data when if you have the data, but that doesn't have the pedigree structure in your data, you can actually use the GUI to construct the pedigree structure there. So how you do it is actually right at the beginning of the stage, when it's asking what type of a project you want to do, you can actually specify the first option that I am creating a new SAGE project, but doesn't have all pedigree data field required with this for the SAGE. So you can actually click this one. Then the window pops up in here. You can actually specify which two people in here are the father offspring, mother offspring. So by clicking this and this individual, you can say these are the spouses, like that. So then it will actually create those parents fields that is required by the SAGE for some many analysis. That's how you work. You make your pedigree file. Okay. And in case you have the pedigree structure now, but the second option on the new project, but doesn't have the parameter file to go with it, you can actually select the second option. I have all pedigree data required by SAGE, but no parameter file. Then what SAGE does is it brings in all the field that exist in your pedigree file, and then it will ask you to specify what types of this column is. Like for example, first column in the pedigree file, it says family, but you don't have the parameter file to go with it. And you can click right here, unspecified, and it will actually give you a drop-down list of the variable type, and then you can specify that is the pedigree ID, and then second one, that is the individual ID, and the third one, that is the parent ID field, sex. So I will actually show you in live just a little bit later. Okay, that's how you can also import the data with the pedigree structure. And then now the person will explain
All right.
parameter file is.
What is a pedigree, a parameter file? Well, it's a text file to record user-selected options for the SAGE program. And you can see it's made up of blocks. And we see in this one, we see a pedigree block. And then later on, we see a marker block. The block starts with a brace and ends with a brace. So can we go forward, please? So as I say, it's just a text file to record user-selected options for the SAGE program. So there are different field types in it. And the different types are, there's the pedigree structure, and you can see that in the about five rows down, you see pedigree ID equals family, individual ID equals IND. So that means when you say family, you mean what what in general we call pedigree ID, and when you say IND, you mean the individual's ID, and you've got father and mother and sex field. Okay. And then you have, after that, you have the trait, and it tells you here the trait equals affection, binary, affected A, unaffected U, missing dot. So now you've defined, you've said that you want your trait to be a binary one with the values A for affected, U for unaffected, and dot for missing. Then you've got age at exam, you've got age of onset, DBH, this, that, and the other. These are phenotypes and covariates. So what's the difference between a phenotype and a covariate? I think basically, as I said before, use the word trait if you want it to be the dependent trait that's or traits that are analyzed in every particular analysis run. Otherwise, call it phenotype or covariate. And then you can see towards the bottom on the left, it has an opening brace and a closing brace. And this is the block that tells you about the marker and alleles. It tells you that this is going to be what we should call later on a one column format, and that the slash is the delimiter between the two alleles, and a missing allele is a dot. And we've talked about a trait marker, I think, as well. So let us talk about some facts about pedigree data and parameter files. Yeah, I've already mentioned what is the difference between a trait and a covariate. Use covariate for anything you want, anything, and specifically for covariates and predictors and analysis. But when you use the word trait, it's used as a major dependent variable, and it's program specific. The program will tell you, some programs will automatically analyze one trait after another. So you only use the word trait if you intend it to be used for all default analyses to be performed with this variant. So now let us talk about creating new variables in S.A.G.E. This is one of the features of S.A.G.E that is really, when you get to know it, it will really help you. You can create new variables, traits or covariates. You can create them as a function of existing pedigree variables. The function parameters may appear anywhere in the parameter file. You can just put them anywhere you like, but they are processed in the order in which they appear immediately after the pedigree data are read in. And the other thing is, the variables created by previous functions can be used in the specification of subsequent functions. Once you've created a variable, as far as S.A.G.E is concerned, it's already there. You can use it in another variable. And marker functions are also available, such as telling you a marker is dominant, recessive, or additive. So let's look at what operators are, function operators you can use. There's a real whole function of them. A negative sign, a dash is just unary negation. 2 stars is exponentiation. The percentage is modulus. The slash is division. The negative is subtraction. A star is multiplication. Plus is addition. Not is logical negation. And the and is logical and intersection. These two, and also the or, logical or, will come up at the end with a 1 or 0, according to whether what you're saying after these nots, ands, and ors. In this second column, we see that for not equal, you can either put an exclamation mark equal, or you can put in a first a less than followed by a greater than sign. This is most important. It's in green to remind you, if you want to say equal to, you must have 2 equal signs. One will not do it. It has to be 2 equal signs. Then the usual symbol for greater than, the usual symbol for less than, and you can see greater than or equal to, it's sort of what you might expect, and less than or equal to is also what you might expect. You can also include some constants. You can include any rational number, 5, 1.23, whatever you want. You can also write E and get the base of the natural logarithms, 2.7828, so on, and pi, 3.15159, so on. That means you cannot call any trait E or pi. They are reserved for those particular functions. So you can bring them up whenever you want. Don't try and call a new trait E or pi. It won't work. You can have lots of elementary functions, and the following are the elementary functions you can use, and they all look pretty much what they are. You put exp parenthesis x close parenthesis, that's e to the power of x. You put log parenthesis x close parenthesis, that's the natural log of x. If, however, you write log 10x, then it's log to the basis 10 of x. Power xy is x to the power y. Squared, if you want to call it x, is just the square root of x. Fabs x is the absolute value of x. Ceiling x or ceil x is the I should say ceil. You can't write ceiling. You have to write ceil, C-E-I-L x. It's the smallest integer greater than or equal to x for any x. Floor x is the largest integer less than or equal to x for any x. Min x is just the smallest x for all the x's you've got. Max x is the largest. In the set that you write min and you write a set of n x's, x1, x2, x3, n, xn, and so on, it just picks out the smallest one, and max picks out the largest one. Note, these are taken directly from the Python library. Okay, now let's see some examples. So this first one is very simple. It says, okay, I want to make a trait equal to x. In other words, from now on, I will use the symbol x. That's going to be the name of my trait. And expression means it will be equal to log of HDL minus log of LDL. So log of LDL and HDL are already variables in the S.A.G.E, in your data file, and you are creating a new trait so that whenever from now on you say X, you will just mean log HDL minus log LDL. The second one is also very interesting. So it says time limit 2. That means if it takes more than 2 seconds, it won't do it for you. That's just to stop it going on forever if you're asking for something stupid. So this creates a new variable. So first of all, you say, I'm going to have a trait called gamma, a trait called constant. And I'm going to sort of define a constant, which is called gamma, and it will be 0.275. And then I'm going to define a covariant, which is an average, provided H1 plus H2 over 2 is greater than gamma. So these 3 lines, they create a variable average whose value is 1 if H1 plus H2 divided by 2 is greater than 0.275. Otherwise, this variable will be 0. I think you take over now, right, Gunju?
Yes. Yeah. Yes. Okay, now I will go briefly to the slides, how to actually create a new variable using the tools on the GUI. So how you do that is first you actually go to the tool options up there, and then it'll show the drop-down list, and then you actually go to the create new variables. Okay, then it does brings up this new pop-up window there. What you do is, since you are creating a new variable, you click this add button right there. Then it actually shows this. It brings to this pop-up window again. Now what you want to do is actually type in your new variable name right there. So we'll call it, as you can see in the next, we'll call it high risk. Okay, then click the existing variable because we want to actually create a new variable name with this example called high risk using the Gleason score that exists in your Pedigree file, your data file. So click the existing variable, then it will list out what types of it. So it's okay. You just list all available, and then you actually select the Gleason score right there. Okay, and then you want to find your operator, how you want to actually define your high risk. So we want to go to the operator, and you want to do the comparison, then select the greater than equal to and type your number 8 right there. Okay, so we are defining high risk being a Gleason score greater than equal. Okay, then now we have this new variable called high risk. Expression is Gleason score greater than equal to 8, and the type will be the covariate. Now click add. That's how you actually create a new variables.
All right. Any questions? I take it either you understand everything or there's so much you don't understand anything, one or the other. But I want to show you now something very useful. And this is all part of function. Generating mean adjusted, variance adjusted, and standardized trait values. This is one of the things you should do fairly early on, I think, is read that whole section. I think it's 3.2.7 in the manual to see just exactly what you can do. I've mentioned a lot of what you can do, but there are so much that you need to get used to it. So this creates from a given trait, covariates or phenotypes, it creates a mean adjusted value. In other words, it goes to your sample, takes off the mean, so it's mean adjusted. Or a variance adjusted value. In other words, it goes to your sample, calculates the standard deviation, divides every trait by its standard deviation. Or it creates what people call a Z-score, both mean and variance adjusted. But also, and this is the neat thing, it can be generated specific to a class of individuals. So this value that you have created can then be used in an analysis as any other variable created with function. It's just always there. Remember, once you've created this thing, it's there and you can use it. You can even use it to make other variables. Just so long as you all these, as I said before, they won't be actually in your data file until after you've read in the data. You won't be able to see them, but they're there. And I will stress that it's very easy to make mistakes when you're doing this kind of thing. So you should always look at, especially when you're creating new variables, you should always look at the .inf file first, which will show you whether you're getting your variables right or not. Let's look at an example of this. At the top, we have function trait. We were going to call a trait. We're going to call it age underscore class 1. And it will be, now you see this, it says expression equals that. So what it's saying is, this is a logical equal because there's not two equal signs. What it's going to say is it's going to be 1 if the age in this class is less than 10, less than or equal to 10, 0 otherwise. Then you're going to make another trait. You're going to call it age underscore class 2. And this is going to equal 1 if age lies between 10 and 20. Notice it's greater than 10 and less than or equal to 20. Okay. And we're assuming all the ages are integers here because for these classes, they have to encompass all the numbers in your data. And it'll create a 1 if age is, I say, greater than 10 or less than equal to 20. It will also, in the third line, it'll create a trait that will be called age underscore class 3 if the age is greater than 20. And this trait is going to be 1 if age is greater than 20, 0 otherwise. Then it's going to look at a trait that you have in your data, and it's been called LNIGE, log IGE, and it's going to mean adjust it. All right. And you're going to call this trait, log LNIGE mean adjusted. And what's it going to equal? Well, it's going to equal this expression. It's going to be a mean adjusted. That's one of the things you can say. You can say, I want mean adjusted. This age in parentheses, first age, is the classification variable. And it's going to take LNIGE at these different age classes, and it's going to mean age adjust them within each class. That's what this whole line means here. The 30 is a very interesting number. That 30 is telling it, you know, I want to make sure there's at least 30 individuals in each class. And there may not be, because if there were less than 30, well, you probably wouldn't think that a mean on the basis of 10 individuals is a good thing to age adjust by. So what this 30 says, it says, well, if you don't have 30 in a class, I want you to borrow from classes next door. So if in age class 1, there aren't 30 individuals, it'll borrow some individuals, as it were, from age class 2 until it's got up to 30 and use that. If it's in age class 2, it'll borrow some from age class 1 and some from age class 3 until it's got 30 and use that. And similarly, if it's age class 3, it will borrow some from class 2. The borrowing really means you're taking some of that information. So it's sort of like smoothing a little bit. But remember, you are only at the end of this, there's only going to be 3 classes for which there's age adjustment. So typically, you would probably want to have lots of classes, so it's not so that the class means are close to each other, if you like. But you don't have to worry if there's less than 30 in any one, because it will do this, as I say, borrowing. And you can read in the manual the details of this, but it's basically, when I say borrow, it's basically what I say. And then underneath, you see, you can say, okay, the next function could be the log IGE variable, variance adjusted. And so what that will be, it'll divide by the standard deviation separately for each of these 3 classes. But if there isn't at least 30 in each class, it will borrow from a neighboring class to make it up to 30. And similarly, you've got in the third function, you're going to get this trait, you're going to call it's going to be Z adjusted, LNIGE Z adjusted, and it's going to be a Z score for all these in the same way, doing it separately for each class, taking away the mean and dividing by a standard deviation, but making sure you have in effect at least 30 individuals to do this for each time you get a Z score. So that 30 is the bin size, and I think that makes that very clear. I mean, it's easy to get this wrong, but if you look at this and the examples in the manual, you'll soon get the hang of it. Okay, we go on with another example. And here we have it. And we see the 5th individual as pedigree ID is 3001, individual ID is 4. That's in the 5th line. Age 10, and the LNIG is 4.159. And if you go across after age adjusting, it's 0.44. After mean adjusting, after mean adjustment, it's 0.447. By the way, you don't have to adjust within classes. You can do it for the whole sample without having these classifications, but it makes sense to have a lot of classifications. because if you could, you would probably want to simultaneously, do an age adjustment by linear regression. Well, this is a cheap way of doing it without doing the linear regression, if you like. Okay. A few notes on these created variables. You can create quantitative variables from marker data. As I said before, you can say, I want it to be dominant, I want it to be recessive, or I want it to be additive, and it will create variables that basically say that. We'll talk about that later. It can create a variable to test for parent of origin effects without marker data, which is really interesting how it does that. So you'll know whether it's maternal or paternal, and you don't have to, and you know that just from the data structure and knowing the sexes of all the individuals. It will also generate a transmitted allele indicator. We'll see how that is exceedingly useful for certain tests later on. For all functions, whatever the type, if there's a missing value in any of the variables in the function expressions, then any variables, then in the function expression will result in a missing value for the function variable. Obviously, I mean, it can't calculate it, so it'll be missing. If any one of the things it needs is missing, then the thing itself is missing. A missing value in any of the variables in a function expression will result in a missing value for the function variable. That says it in a nutshell. And once created, these variables may be used just like traits, phenotypes, or carriers read in from the pedigree data. And as I said before, I think once, these variables are not currently physically added to your pedigree file, but are stored internally and will be used as soon as you've read all the data in. The information file contains the new variables, and you should always look at the information file, the .inf, to verify that the function is performing the way you wanted it to be. Okay, let me see. Oh, here's an overview of the S.A.G.E programs, and it's particularly the S.A.G.E GUI, graphical user interface. You'll see the top 4 programs are data summary and quality. The next 2 programs for aggregation and segregation. Next set of programs are model-free linkage. And then there's the 2 for model-based linkage. And then there's the association programs. And I think I already mentioned this. Despair is an online-based program for if you want to. In the old days, we would do 2-stage linkage analysis with pairs of, so this is designed for pairs and for linkage analysis, and this would help you design the 2 stages to minimize the amount of money in a way that you have to use to type all your markers. Okay, so let me summarize in specifically each program. PedInfo generates summary statistics on pedigree data. It does it for the whole sample, for just the structure. It also does it for specific traits or covariates within that structure. Then we have F-core. It calculates familial correlations. So that's the first way of determining whether you have aggregation of a trait in a file. Segreg performs commingling and segregation analysis. Commingling just asks, do you have 2 or 3 distributions? And if you do, you may ask, do they segregate in a Mendelian fashion? That's Segreg. Marker info detects and reports Mendelian inconsistencies. Unfortunately, no data are perfect. And one of the things we want to do right at the beginning is it possible that our markers are not consistent with Mendelian inheritance, because if they are not, then of course we want to do something first and make them in some way consistent before we go any further. Freq, it calculates allele frequencies, inbreeding coefficients, and it prepares what we call a locus description file, which will be used in other programs. So the allele frequencies, typically when we're doing, certainly when we're doing linkage analysis, perhaps other programs too, you need to know what the allele frequencies are in the population. And it will also check whether there's inbreeding coefficients, whether they're non-zero or not. GenIBD is a program which generates single and multi-point identity by descent sharing estimates and prepares these identity by descent files, which is used for other programs. I suppose one could use it by itself for in some instances, but it's mainly something you'll put into other programs. Rel test suggests true relationships in the place of putative relationships. You've said you have SIB pairs or monozygotic twins or half. Well, typically you'll probably think this is most of the time. This is for when you say you have SIB pairs, and it'll check: do you really have SIB pairs, or do you have half SIB pairs, or do you have monozygotic twins? And it's a very useful program. It gives pretty output, I suppose, histograms that really are very informative just by looking at them. Then we have SIBPAL. SIBPAL is the main program for performing model-free linkage analysis on SIB ships. Originally both SIB ships and half SIB ships. Now you should only use it, even though it will work for half SIB ships, you only use it for full SIB ships. RelPal performs model-free linkage analysis on extended pedigrees. And if you have half SIBs, you should really use RelPal, not SIBPal. SIBPal was originally used before RelPal was ever developed. LODPAL performs all types of affected relative pairs using the conditional logistic regression. We're going to talk quite a bit about that, at least on the fourth day, but there are difficulties and we will mention those difficulties with it. LODLink performs single marker model-based linkage analysis. This is what we call it, single marker, because there's single marker and a trait. There's one marker and a trait. But this is what years and years ago we always called two-point analysis. It was two-point because there was the marker and the trait, and the trait was somewhere. And so what we call single marker is what everybody used to call two-point. Okay, well, because there's only one marker and the other thing is a trait. MLOD is multi-point model-based linkage analysis. And that was developed, I suppose, from LODLink. Originally, we started realizing it's better to have a whole map of markers. We can get more power that way to place a particular trait on a map. S.A.G.E is association analysis. And it basically looks for association between any two things you want, but it could well be a marker or a SNP and some trait. And it does this for family data. Therefore, it allows for familial variance components. And this is what S.A.G.E was derived for in the first place. But then we realized that these familial variance components could provide estimates of heritability, whether heritability in the narrow sense, broad sense, or locus specific heritability. All these are possibilities, though the program was originally only association analysis, but doing association analysis from pedigrees, not from case control data and things like that. TDTX, it basically, as an exact, the X is exact for the TDT test. And the TDT test, as we'll discuss quite a bit, it determines if there's, it's called the transmission disequilibrium test for detecting linkage in the presence of allelic association. It'll also test for allelic association in the presence of linkage. And this is basically linkage disequilibrium. And there's a whole slew of TDT tests available. And this one will do the asymptotic ones and the exact ones, though when I say exact, it will do it by sampling the distribution rather than from the, it's exact so long as you take enough, a big enough sample from the whole of the output distributions. And then there's A.G.E. A.G.E. was an add-on program, and it estimates the distribution of age of onset for a censored trait, and hence individual susceptibilities. We'll talk about susceptibilities when we talk about age of onset analyses of segregation analyses allowing for age of onset. And finally, there is Decipher, which estimates haplotype frequencies. And if you have haplotypes these days, if you have large pedigrees and you can get haplotypes, you can get more information for doing your association analyses. And I will just mention despair. It's not in the, in fact, it's not even, I don't know if it's in the user manual or not, but it was an online program that we devised at a time when linkage analysis was rampant, and we wanted to design the cheapest possible design, two-stage design, when we had relative pairs and we were doing simple analyses from these pairs. So I think that's it. Any questions? Well, I will see you whenever the next day is.